Okay, hello everyone, and welcome to my presentation in which I will talk about the evolution of melodies. In class, we discussed a lot of possible theories why there is music, trying to answer the question of what the evolutionary function of music is. Examples of these theories is that music functions as grooming or as sexual selection, etc. However, in this presentation, I will offer a more mechanistic perspective on how music changes over generations in an iterated fashion. Um, to introduce the subject, I will first show you a video.
Okay. All right, so let's have Matthew then start.
Go back.
Okay, I think the point is clear, even though it's in a different modality, namely sign language. I think everybody has played this game in his life. What is nice about this game is that it functions as a model of cultural transmission of music over multiple generations. So people taking part in this game can together be viewed as a culture, each person alone as a generation, and the message that they are conveying can be seen as the language, or sorry, as the music that's undergoing changes over time. More interesting is to know how these changes between the students occurred. Is it just pure randomness? Um, or are there maybe individual listening or memory errors? Perhaps it's not at all random variations, and there might be a certain pattern that we can identify in this process. And that's what I will discuss in my presentation. My claim is that there are actually two specific principles that guide the changing of melodies over generations. These principles are one, the motor constraint theory, which says that we are limited by the movements that we can make in our vocal tract. And secondly, statistical learning, that we learn music in a statistical fashion. And that we are constrained by our memory storage. Well, I will go over some papers discussing these claims. First, Shanahan did both a lab experiment study as a corpus-based study on oral transmission. In his lab, participants were musical experts who had to listen to stimuli such as the following sounds. Sorry, yeah.
La 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 la.
Then they listened to the sounds and they had to reproduce it while being recorded. Then the recording was shown to the next participant, and this followed until all four participants listened to it and recorded their own singing. Well, based on Spitzer's theory of pentatonicism, stating that music is based on the pentatonic scale, Shanahan predicted that the songs would change over generations, becoming more pentatonic. And therefore, he predicted that the 7-to-1 cadence would transform into 2-to-1 cadence. Then, music theory alert. Cadence is the ending of a song. So there are many different cadences, and most music progression starts with the tonic, so that's the first chord of a key, and they also end with the same chord. They also say that this is like coming home or closure of a certain chord progression. In Shanahan, the following chord progression was used. In the key of C minor, this is a 7-to-1 cadence. In the C key of C minor, this is a 2-to-1 cadence. So this becomes this. Okay, so sorry, results show that indeed the 7-to-1 ending gets removed for a second to one ending, and these in these focal learners. Also in the corpus study, in which music over generations was compared as sequence of notes, shows that phenomenon shows that this also occurs for longer periods of time. As the second tone chord is closer to the tonic than the seventh, these results give some solid evidence for the motor constraint theory. The motor constraint theory, as I stated earlier, states that music changes according to the physical limitations of our vocal tract. Notes that are close to each other in the chromatic scales are also close to each other in our vocal tract. Therefore, it takes less effort to switch from, for example, B to a C than, let's say, a B to a G. And this can also be seen in this graph here. This is participant A, participant B, participant C, and D. And here the 7-to-1 becomes a 2-to-1, just like Savage predicted. Savage provides even more evidence for the principle of least effort that I just proposed. He did a comparative study between English and Japanese speakers. Using algorithms that could order the similarity of notes, pairs of songs were created and analyzed. Two main findings followed. One, notes with stronger rhythmic functions are less likely to change. This can be seen in the graph. Bold are rhythmic notes. Secondly, note substitutes are more likely between full neighboring notes, and this can be seen in this graph. So notes at neighbor, and I talk about full notes because that means that there are two semitones away from each other. These can substitute each other without the body of the music changing too much, so like the melody stays. Well, this also supports the motor constraint theory or the principle of least effort, as again, notes that are close by are physically easier to follow each other, but it could also be to statistical learning. The statistical most relevant notes are the ones that are only remembered. So in conclusion, as can be seen, the motor theory provides a valid mechanistic account of transmission of music, integrating the structure of our vocal tract with our bias for certain musical progressions, such as the pentatonic scale. There is basically this perfect interplay between motor movements and pentatonics. One explains the others, and the other way around. Statistical learning of music is also very interesting because it is a given fact that people have a limited storage and the whole piece of music can be learned as a whole. However, it's very difficult to say whether music change is due to the motor constraints or due to our memory constraints. Therefore, at least in the article, statistical learning is more of a confounder. Thanks for listening. That was my presentation.